In this video, I would like to continue the discussion of fluid properties. As all you know that we talk about fluids that deform continuously when shear stress is applied. So I would like to further elaborate the definition of shear stress and the deformation. Deformation usually represent in terms of the rate of deformation. Now shear stress we usually indicate with a symbol of tau to shear stress, and it is as you know that the shear force that acts among the layers of the fluid and divided by the area onto which it is acting. So shear stress is shear force divided by the area onto which that force is acting. And the rate of deformation, first understand that deformation we indicate with a symbol called gamma, and rate of deformation is simply the change in the value of gamma with respect to time. Now we are ready to distinguish between two important class of fluids. One is called the Newtonian fluid and other one is known as the non-Newtonian fluid, and we perform that distinction between these two on the basis of the nature of deformation curve, which can be plotted between the shear stress and the rate of deformation. So for example, if I show you here in this, if I go and take tau on the y-axis and rate of deformation partial gamma over partial t, then for Newtonian fluid it will be a straight line. However, for my non-Newtonian fluid it will be a non-linear curve. Now finally, I would like to make a comparison between the deformation curves of solid and fluids. So if you see that if I go and plot the shear and strain for solid, because all you know that solid they go and deform and under the action of forces, and that deformation will be permanent at a certain point. So after that there will be no recovery in the shape of the solid. So curve will be look like that on the left hand side. However, for the fluid, if you see the right hand side, it is a straight line and it will come back to its original shape if I go and remove the forces. Now I would like to describe here another important property of the fluid, which is commonly known as density, or indicated by a symbol called rho. And the density of fluid is nothing but the mass of the fluid per unit volume. And the unit of density in SI system is kilogram per meter cube, and in the FPS system it is slugs per feet cube. Here I would like to define the definition of a specific weight. A specific weight is a weight of the fluid and divided by its volume. And now here in this regard I would like to relate the specific weight with the density. As you know that weight is equal to mass into the gravity, and utilizing the definition of density, the mass can be represented by the product of density and volume. So in this regard we can cancel the volume, and a specific weight will be our density multiply by the gravity, which will be represented in terms of the symbolic form as so that is the definition. Here make sure that the gamma is utilized to indicate the specific weight. Another important definition that we will be utilizing is called the specific gravity. So specific gravity is nothing but the density of the fluid of a particular fluid divided by the density of the water. So in this way you will calculate the specific gravity, and it is a ratio. Our next topic is the equation of state, which is a relationship between the composition of fluid. In fact, it is a relation among the temperature, pressure and density of the fluid. And for a thermally perfect gas, the equation of state is written as P equal to rho RT, where R, capital R, is known as the gas constant. And it has different values for different gases. And it can be related to the universal gas constant divided by the molecular weight of that particular fluid. And it is important to note that the pressure and temperature should be the absolute quantities in this equation.